Hello again, everyone. I realized as soon as I submitted that video that I forgot a really important third case for partial fraction decomposition. And that's what I get for making a video without a script. So without further ado, let me introduce this third very important case. So this final case is going to be when we have repeated zeros in the denominator. And so an example of this would be something along the lines of, let's say, f of x equals 3 over x times x minus 3 squared. So in the denominator, we have these two significant factors. We have x, which is a single zero, but then we have a double zero of 3 with the x minus 3 squared term. The really easy way to deal with this is we're going to expand about both zeros in terms of x minus 3, the multiplicity of both zeros. So we're going to have a denominator of x in our expansion, a denominator of x minus 3 in our expansion, and to account for the multiplicity of this zero, this factor of x minus 3, we're also going to include a factor of x minus 3 squared. It might seem a little redundant to expand on that twice, but again, the squared is sort of an indicator telling us that we have this multiplicity, that we have this second zero we have to consider, and we might possibly have to deal with this as a quadratic. So the nice news is that we're still going to assume all of these are just constant terms. That last one might be a little surprising because it is a quadratic, but it is a reducible quadratic. We would only ever have a linear factor, something like the form cx plus d with a quadratic in the denominator, if it was a second degree polynomial that was irreducible over the real numbers, if it was unfactorable. This is factorable. So we're just going to proceed as normal. We're going to multiply by everything that we're missing. So I'm going to multiply this first one by x minus 3 squared. This second one will be multiplied by x and x minus 3, because we only have one of them right now. This third one will be multiplied by x. So upon doing that, we get 3 across all the numerators, because now the denominators will all be equal. 3 equals a times x minus 3 squared plus bx times x minus 3 plus cx. And I'm just going to expand out some more of these terms. So using the binomial theorem, this would become a times x squared minus 6x plus 9. Expanding this out, that would be plus bx squared minus 3bx. And this would be plus cx. Finally, we have 3 equals ax squared minus 6ax plus 9a plus bx squared minus 3bx plus cx. And let's just collect all our terms. So the only second degree terms we have on the right-hand side are ax squared and bx squared. We don't have any on the left-hand side, so this means that a plus b must equal 0. We also have, in terms of x terms, we do have 3 of those. We have negative 6ax, negative 3bx, and cx. We have none on the left-hand side, so this means the coefficients all must add to 0. So c minus 6a minus 3b equals 0. Finally, the only constant that we have is 9a on the right-hand side. We have 3 on the left-hand side, so that has to mean 3 equals 9a. And that gives us kind of a freebie. This means that if I divide both sides by 9, a is 3/9 or 1/3. So we have that. Because a plus b equals 0, this must mean that b is negative 1/3. And finally, we can make all of these substitutions into this last equation, because now we know 2 of these unknowns, we can just solve for the third one. This would give us c minus 6 times 1/3 is 2, minus 3 times negative 1/3 would be plus 1 equals 0. So that gives us c minus 1 equals 0, which means c is 1. So finally, this means that our original term, which is 3 over x times x minus 3 squared, equals 1/3 over x plus negative 1/3 over x minus 3 plus 1 over x minus 3 squared. And there we have it, our final answer. Hopefully this makes sense as well. I apologize again for leaving that out on the first video. I'm definitely gonna remind myself that I need to include all of the important cases. That is a really important one. It comes up a lot. It's honestly, in my opinion, the trickiest one. It's the questions they'll design to try to trip you up and catch you. So if you have any questions or concerns, definitely don't be a stranger, and I will see you soon.